Hello, everybody. We are live now, I guess. Maybe people can text here in the chat so we know that everything is working fine. Marina, welcome to the e-pint of chemometrics. It's such a pleasure to have you here as our guest of the third e-pint of chemometrics. And it's really nice to know whatever you want to tell us about chemometrics. So thank you for the invitation to accept the invitation.
Thank you, Carol, and for invitation. I am very pleased, and I like this kind of event, especially in this period. It's very nice to have the occasion to stay together in a certain sense. I mean.
Yeah, that's perfect. Okay, so let me just introduce Marina for those who doesn't know. Marina Cocchi is an associate professor at the University of Modena in Reggio Emilia. She authored more than 100 publications on international journals and books in the topics of multivariate, multi-way, multi-set methods, data fusion, feature selection, MSPC, food authenticity, multivariate calibration, experimental design, chemical fingerprinting by spectroscopy, and chromatography. She has supervised many doctoral and master theses, and she participated in different committees and editorial boards. Moreover, she is an excellent researcher and an amazing person that will join us today. Thank you, Marina, so much for your time. I want to tell everyone that we will have a certificate of attendance today. So you just wait in more or less 15 minutes. We will start to put the link to a Google form, okay, in the chat, and you'll be able to access that link and subscribe to get your certificate. Okay, for those who need it. And in any case, if you need, you can also always write us in our email that we also put our address here. Okay, so cheers, everyone. I hope everyone is having...
Cheers!
Yeah, cheers. And wait. Cheers. And now, Marina, you have the screen for you, and you can start whenever you want. Okay, I'll be here in the background, and anything you need, just let us know. Okay, so
okay,
please,
okay,
you have the word.
okay. Thank you very much, Carol, and for a very nice invitation and very nice initiative. And I hope it will be not too boring for you to listen to me. I sort of wanted to reshape my presentation somehow, but this is a crazy and active period with all the teaching duties. So in the end, I didn't manage. But anyhow, I'm going to talk a bit about data fusion, and this is maybe a rather fancy and in fashion word nowadays. And the perspective I will give to this talk is to maybe let you know that there are several methodologies that maybe we do not call data fusion methodology, but actually they do data fusion, and also that as in any chemometrics, let's say, and in any chemometrics methodology or approaches, also in data fusion, there are three things which are important. And the first thing is data. The second thing is question. you want to answer. And the third thing is validation. So there is really nothing especially new with data fusion with respect to what we usually focus our attention on. Okay, so that's the point of view I will share with you today. And a bit of motivation or context. We all know that in the last, maybe, I don't know, maybe 20, maybe 30 years, maybe 10 years, that depends on how you want to judge it. But for sure, our job as a scientist has changed quite a lot, because we use more and more instrumentation, and we are somehow also acquiring data in a faster way, in a less destructive way, meaning that once maybe to gather data was a sort of the bottleneck in scientific research, and nowadays is not. I mean, and maybe the bottleneck is how to timely actually analyze the data we get. And also our approach has a bit changed. Now we are more and more sort of using data-driven discovery paradigm in science. And this means that somehow what we do every day is to characterize as much as possible the matrix, the system, the samples we want to study, and try to combine this information in a meaningful way. And so we may say that data fusion methods are the method which allow us to integrate data that comes from different sources. And if we think a bit about data fusion, we may go back to our mind and actually understand that we are fusing data all the times, because we gather information for our senses, and we translate this information, or we fuse this information in our mind in many nice ideas. And so this is something we really do every minute. Maybe we don't realize, but every minute we are fusing information that comes from different sources. And we aim to do this also with our fancy and nice instrumentation. And here are just few fields where you really need to characterize broadly your data. For instance, a medical diagnosis is based on the result of very different tests, and some may give you complicated spectra or image, some may give you just few numbers, and some may give you just written sentences. And the same when people predict the weather forecast, uses a lot of physical information. And we do this in food authenticity, in foodomics, and also maybe we do not explore this too much, but also we have text on the web, which is not only connected to social media, but also to source of scientific information. Can be the scientific journal, can be opinion or forum or whatever, and this is also a field that can be explored. So that's mainly the reason why we are interested in methods to integrate different data, and why and what we aim to reach by fusing different data. There are different, let's say, different reasons that maybe are more important depending on which scientific community is speaking about data fusion. For instance, one aim can be improving decision, especially automatic decision. And in this case, the source of information are basically sensor. And for instance, a car that goes without driver or any robotic application needs to have a nice decision and to fuse information for several sensors that gives an idea of what is around, what the car should avoid, at which speed should move, when should stop, when something appear. So the let's say more electronic engineering community is interested in decision making, automatic decision making. In remote sensing, the idea is that fusing data at different spatial or spectral or temporal resolution may improve the drawing of a scene and to know what is on the scene, looking for from far away. So in this case also, the idea is that we can get better resolution or a better view of a scene if we integrate different sources of data and imaging data. Another is the idea that we can improve somehow the management of the knowledge, and we can fuse heterogeneous like text with numerical or relational information, and we can maybe fuse data that are flowing in time. And there are a lot of applications also in this context, which is the context that we use in developing mobile app, social media, the sensor embedded into object like the barcode, wearable sensor. In this case, we can have a lot of flowing data. So maybe the source of the data is not different, but they are flowing at different time, so they are, in a certain sense, different data set. This is also a context. But maybe the context that is more studied or more of interest for chemometrician is to use data fusion to enhance understanding and problem solving. So what we aim is to get improved model. So in this case, the focus is to analyze jointly data sets which are different because they came eventually from different analytical platform, or because they came partly from instrumentation and maybe partly from, I don't know, sensory analysis or whatever you have in mind. And in this case, we may be interested in just getting an improved model, maybe for classification or regression, or we are interested in having a better exploration of our data and maybe assessing what is common or what is distinctive in different data sets, and also which is the relationships or the way they are related to each other. So eventually, in chemometrics, I think we mostly use data fusion in this context, but of course, this is also an interesting area to explore. So general aim, we have already said, gathering enhanced information in a perspective of data-driven knowledge about system phenomena that we observe with different type of instrumental technique at different time in different condition or environment, or with the different experimental setup. And important is that the data set that we have in data fusion usually are called with different name, because we can call multi-block data. This is probably the most wide terms, or multiset, or multimodal data, or linked or coupled data. So these are all names that define somehow the fact that I have data from different sources. And data fusion is the bunch of method to perform analysis of this data. So we have to understand this data and the nature of this data to do or to choose the right methodology or the suitable methodology. And so important aspect is understanding nature and structure of our data, and clearly have in mind which are the research questions that we want to answer, because depending on the question, the route to get an answer may differ. So as I was telling in the beginning, this is really the most important things, to understand the data and to clearly state the research question. So I think that especially, I mean, in chemometrics, when one, but not only in chemometrics, we know that we have some sort of taxonomy of data fusion, and we speak about low level, mid level, and high level. And this is just a cartoon, because I sort of was thinking that when I was little and when you do math, somehow the teacher comes and tells to you that you cannot count apple with pear, and maybe not even with orange, but in a certain sense, when we do data fusion, this is what we do. We take data of different nature and we analyze them together or jointly. And we can do this at different level. So we can just use the data as such. And this is the low level. So we somehow built a model by mixing the data, but without doing almost anything on the data. We can be at mid-level when we extract features, and we can have from our data and then fuse the features. And we can do this at different level, because we can just take part of our data, like when we do variable selection, or we can compress our data with some methodology. So we can model a little bit our data in separately. In this case, for instance, we prepare candies, and then we can fuse them and obtain a model. And then we have what is called the high level, and in this case, we do not fuse the data, we do not fuse the features, we fuse the models that we built on each single bunch of data. So in this example, for instance, we use a regression model to estimate some properties, some component of our data, and then we mix this different model with some consensus strategies to assess the final content. So this is one framework which is very, very common in presenting data fusion, just to remember us that we may fuse the data or the features or the model. And of course, there are different implications when we do these kind of things. So going a bit more formally, doing low level means that we can simply augment our data, and augmenting our data, we have to find a way to make our data block to fit. So they should have a dimension in common, and we have also to find a way to let each block to contribute in a fair way to our data analysis. So these are, let's say, the main things that we have, or the main issue that we have to consider. But also at low level, we have several methods, which are called the multi-block, because they operate on different blocks, and this can directly operate the composition on joint, and also in this case, we should have some dimension or something that links our data, not necessarily a dimension. And we will see a bit this framework just to give you a flavor. And when we do mid-level, we can do data reduction, or we can extract features. And so basically we fuse the features. So we can have a block of any dimension. As far as we have a one dimension in common, we can extract feature from each blocks, and then we can go back. It's a sort of low-level data fusion in features. And when we do high level, we use a modeling technique in a separate way, in a distinct way for each block. And we obtain a result. We usually call this result also a decision, because maybe we classify the sample in this block, and so here we have the class information. And then we classify the same sample, but with a different set of data, and we have a second decision, and so on and so on. So what we fuse in this case are the different decisions. So in this case, we have to apply a distinct model on each data block. And in the more electronic community, they call this tree level. Instead of level, they call level of abstraction. So there are other communities that are also very active in data fusion with a different perspective with respect to schemometrician. This is also something to know. Okay, I think this is mostly what I want you to somehow share with you. And it is to understand that when we say that we work either at low level or a mid level or at high level, we are somehow simplifying, but we can mix this level if we have complex data in different way. So what I try to propose to you with this slide is a bit the fact that when you start that analysis, before actually going to that analysis, you can think a bit of the strategy you want to apply, and think if this strategy is the one you need, or the strategy that better suit your problem. It's like when you want to write a code, maybe it's better if you take a piece of paper first and just with a pencil you sketch the idea of the function you want to implement and why you want to implement. So in this case, I use the green color for the data, I use the red color for the features, and I use the violet for the decision, and I use the solid line for the low-level path, the dotted line for the mid-level path, and the dashed line for the high-level path. So for instance, if we just have B blocks of data which are different, and we augment the data, so we direct go for coupling this data and then do the modeling, somehow this is the low-level path, and then we will have the model outcome. If we go for the, and we have two roads here, because we can use a multi-block method, which I call the coupling, or we can just use the augmentation, which is what is usually called the low-level fusion. And on the other end, if we go for mid-level, we do a modeling step, or because we somehow compress this data. So maybe we apply, I don't know, principal component on this data, or a multivariate curve resolution on this data. So we use a modeling step, but not for obtaining our final model, but as an intermediate step. Or we can simply decide to use some feature and to select some variable. But also, this depends on how we do this step. Because if we use some variable selection method, then again, we do some modeling just to extract the features before actually doing our final model. So we can go for this path that comes through a modeling step. And at this point, once we have the features, we fuse the features, we do our final modeling, and we have the model outcome. When we do the high-level path, we do modeling on each block in a distinct way, or we may go to the features and then we can do modeling on the features. This is also possible. So we can go here and then back. We have the decision or the outcome of this distinct model. So we have the outcome of model for block 1 up to block B, and then we fuse this decision or this information, and we get our final outcome. There is also something that we can do, and this something is that we can transform our data, and we can pass from the variable space to the kernel space. So we can pass to the sample similarity space by using a distance measure, a similarity measure, by using a kernel function. So we can pass from our, let's say, raw space and linear space, maybe to a nonlinear space or a similarity space. So this means that when we go from here to here, we generally go to a sample by sample matrix somehow. Can be also not sample, can be, let's say, representative samples. So not necessarily is sample by samples, can be also, let's say, relevant representative of the density of our sample, so density point or kernel point, but in general is sample to sample. And so we can couple our data after they've been transformed in this way. And in this respect, a common thing is to sum the kernel from different data block and then do a weighting of our block and then model this. So we fuse the kernel of our original block and then we do the modeling. Why I spend some time on this? I spend some time in explaining you all these different routes, because of course they imply a different effort in terms of modeling, and also a different effort in terms of validation of your model, a different effort in terms of updating of your model, and so on. So that's why it's better to know in advance which way you want to go later on. Okay, and we have to understand our data. So we have to understand the structure. And in this case, we speak about homogeneous data when they have the same order. For instance, here we have 2 dimension in our data table, sample and measured variable, and each data block has the same dimension. Here we have a 3-way array, And in this case, they also have the same dimension. And we have a mode which is common. In this case is the sample mode. In this case are two modes in common. So are, for instance, the sample and the occasion, that in this case are patient and time, for instance. In this case, they have the variable in common. So they have the same sensor measured on two different set of sample. Can be, for instance, two stage of a process. And in this case, again, we have two dimension in common. We have, for instance, these are excitation, emission, fluorescence data. So we have the fluorescence landscape in common, and we have two different set of sample. Maybe we have monitored water in two different cities, and so on. We can have also heterogeneous data block, and this means that are, for instance, block of the same order, but they share only one mode, not two, as in this case. They only share one. In this case, they only share the sample mode. In this case, they only share one variable mode. And we can also have a block of different order that are sharing one mode. And it seems that this situation are difficult, and they are more difficult than this for sure. But there are methods that can also handle this situation. So this is also something important to know which data we have, what they have in common, which is the mode by which they are linked together. Okay, so let's speak a bit about low-level data fusion. When they are homogeneous, we can use the decomposition method. And we have a lot of decomposition method that can simultaneously analyze this data. And we have really many of them, and they can be considered under the same framework. So we can call this framework collective matrix factorization. For instance, we can have sum principal component analysis. We can have simultaneous component analysis. There is a method called status that is another method. And the idea is the fact that if we have one mode in common, we can decompose, and we can have the decomposition matrix, in this case will be the score, for this common mode that will be common to all our data block. And then we will have loadings for the variable that are different for each block. And one thing we have to have in mind is that we need to scale this block if we want a fair contribution of each block to the model. And some of these methods do this, some of the methods do this to a less extent. So we are not going deeply in this, but the idea is when I use this methodology, there are so many because they may treat differently the way that they give to each block in the analysis, and they may also treat differently the variance they explain of each block, because there are methods that maybe maximize only the joint variance, method that also maximize the variance explained by each different data block, and there are blocks in which both the score and the loadings are orthogonal, and block in which only part of them are orthogonal or not. So they may differ by the properties of the subspace that they are creating, the common subspace and the single subspace for each block. And these are simultaneously, but there are also multi-block methods which are sequential. So this means that they work a component at a time, like a hierarchical principal component, for instance. When we have n-way array, three-dimensional array, or n-way array in general, we need tensor decomposition methodology. For instance, Parafak or Tucker, or higher order singular value decomposition. So we can handle this with tensor methodology. Okay, so what more? This is just to tell you that when we have a heterogeneous data block, there is a methodology that is based on the fact that, again, we can focus on the mode which is shared, and we can simultaneously decompose our data block, which means that we have a fitness function which is the sum of the fitness function of the single block, imposing the mode which is in common the same decomposition matrix. So for instance, in this case, again, the equivalent of the score matrix is the same in the two functions. And if we have, for instance, a test block that share a different mode, we can add to the loss function another terms, and in these terms will be the third mode, which is in common between this block and this block. So there will be the C that will be common among these two. And we can extend this methodology quite far, and benefiting from the fact that some tensor decomposition method can work with missing data, it has been developed a methodology that fill the different block in a sort of a super array and consider missing the part that are missing and can decompose all these blocks altogether. So these are somehow a different perspective on low-level data fusion. Is more a multi-block or a coupled block, but what you reach in the end is a unique model fusing information from very different data block. Okay. Another important thing is that to ask ourselves, are we interested in only getting a model which use all the information, or are we also interested to assess what the different blocks have in common and what is distinctive among the different data blocks? Because sometimes we don't care, but sometimes we care, because maybe we don't want to use 3 different spectroscopy for characterizing our data. So we want to know if maybe one method can be enough, so which is really distinct, or maybe we have some complex biochemical process and we want to know if using different maybe different instrumentation, we have the same metabolite showing up. So this can be in common, for instance, in an MR or in mass spectrometry. And maybe they have some distinctive metabolite that can be captured only by one type of analysis. And also we may be interested in this. So there are methodologies that are focusing on identifying common and distinctive component. And there are several, but there are basically 2 approaches. One approach is that try to rotate the component in order to follow a sort of preordered structure, where for some block we have 0, so that in this case we can capture what it is distinctive among them. Another approach is to use Sparks method. So we introduce penalty and try to have sparsity in the different block. And also this is a way to have as an output what is common and what is distinctive in the different data block. Let's say, of course, when we use multivariate curve resolution in a multi-set structure, so this means that we can have data that have in common maybe the spectral dimension, like in this case, data set 1 and 2 have in common the spectral dimension. Maybe we can also have a data set that has in common the sample dimension, and multivariate curve resolution is enough flexible that can handle any combination. So can handle just a piece of this, or just a piece of this, or all together, and we will get different decomposition block. And in this case, the assumption or the requirement is that one mode should be common, and we expect the presence of one or some component that are shared by the different data set. So the idea is that we can retrieve some component, some profile that is common, at least one. Otherwise, it doesn't work. And on common component, there is also methodology which use kernel, use the distance, the squared distance. So it is a linear method because you use the square distance. And this is called ComDim, and is quite has been developed in the French chemometric community. And basically, you calculate the covariance in the sample sense matrix of each data block. You sum them in a fused kernel matrix, and then you decompose this matrix. But when you fuse, you use different weight for each block, and these are also called the salience. And this lambda tell us how much each block contribute to the common decomposition. And so the analysis of this lambda that are optimized during the procedure tell us which part, which component are having a contribution, a common contribution from the different block. Okay, I think up to now I have just spoken of one data block, but we may have what is called the asymmetric case. So we may want a block to be the one that all the properties or class membership that we want to predict. And in this case, we also have a lot of multi-block method that we can apply. Okay, so these are the main issue if we work at low level. The scale of the variable, which can be different, and the fact that we can have outlier, the fact that we can have different type of noise in the different block, and the first two issues are normally treated by standard preprocessing, while this issue may be treated in maximum likelihood or Bayesian framework, so this is a bit more tricky. And the main thing is to ensure a fair contribution. And this is done weighting or scaling the block. And one scaling which is used is to divide each block by its norm. This is a very common way if we want to give equal importance. Which is the advantage of low level? That we can interpret the result directly in terms of the original variable. Which is the drawback? That there are no general criteria to decide the number of common and distinctive components. This is still something a bit tricky. People are working on that, and but it is a bit more tricky than with traditional analysis of just one block. When we do mid-level data fusion, we extract features, and we can use feature selection or decomposition method. In both cases, we have to mind validation, because if I have a data table and I want to split this in a training and in a validation set, I have to do this from the very beginning, because otherwise, if I calculate or my feature in all the data and then I split afterwards the fusion, I will have used the information from all my sample. So remember, mind validation. This is the most important things, that if you want to use the model then to predict, to forecast, to do something after, you have to remember that your test set should be completely independent. So this is, I think, the only things to remember. And what is the advantage? That the scaling of the single block is less critical in this case, because we extract features. That we filter noise somehow if we use the composition method, or also if we do variable selection. And a disadvantage is that we do not have anymore the original variable. We have the features. So we have to interpret the features and eventually go back to the original variable. And we have to handle a bit more model, because if we decompose by PCA, we have a PCA model for each block. And when we compare mid-level with the coupled factorization method, so with multi-block or multi-set, what we lose is that we lose a bit the capability of directly pointing to common and distinctive information. But of course, there is the possibility to mix the two things, because we can use feature extraction, and then we can use one of these methods linking the different features we have extracted. So don't be rigid, because we can be really flexible in data fusion. When we do high level, this is something I really don't know very well, because I have never used it. So I know that in this case, you can use different way to mix the decision, and can be just consensus. So the most frequent decision is the final one, or you can use Bayesian inference or other fuzzy set theory, and so on. So there is also here several methodology to combine the decision. And the main issue is when you have conflicting or contradictory information from the different models. And also here, remember that especially because you take decision, again, independent validation. So remember that if you have to do a split, you have to do at the very beginning, okay? You cannot wait. You have to do before applying your model. So I have two examples, but I think I will show you only one. Why? Because it is about beer, so we have to speak about beer and we have to drink a beer. So, and this also is another way of doing fusion of data. This was Nicola. Maybe some of you knows Nicola Cavallini, my past PhD student. He was a student of mine and Rasmus altogether. And he was working with beer. Why? Because he was in Copenhagen. So this is a motivation. And he analyzed like 100 beers. They were all light beer, or in the terms of color, not of alcohol. And they were coming from different parts in the world. So it was acquiring NMR spectroscopy and Vis-Near spectroscopy. And in this case, we didn't have a clear clustering. So our idea was to resort to somehow kernel method. But in this case, so we calculate the similarity, but instead of calculating the similarity of the sample only in one way, we did this in different way. So we apply different methodology to assess the similarity. Basically, we calculate different type of distance and we choose different threshold to establish which sample were close. And we transform this information in adjacency matrix. So 1 means the two samples are close according to a given distance threshold. 0 means they are not close. And we also use not the distance, but self-organizing coordinate map. So if they are in the same neighbor, they get a 1. If they are in a farther neighborship, they get a 0. And we change the level of neighborhood. So in this case, we have a lot of adjacency matrix, and if we fuse them together, and then we did principal component analysis or clustering in this fused data matrix. So this is another way of fusing data. And the result were nice because we were able to see 3 main group of beer. We were able to see small group of beer that had something in common. We were able to see that very fancy, strange beer were distinct from everyone else. And then we notice in a couple of components this nice subgroup. And we didn't know in principle why they were there, but we happened to discover that they were nicely ordered, partly because of the color, of the color trend. So they get more intense in this direction. And also partly based on the score in the liking. So this is a sort of overall liking expressed by consumer on a public database, on a forum, which is called the Rate Beer. And so there is a relationship between the color of this score that goes from low to high, and these groups that we see here. So this small group have different were different liked by the people. So somehow they were meaningful, and we were happy of our idea of fusing data. And I don't know. So that's all, Guy. I want just to remind you that if you want to know more things in a less confused way with respect to my talk today, there is this book where many people has written chapters that are rather interesting. And okay, now is beer time, and I suggest you not to fuse this beer, but to taste one by one. Otherwise, it will be a mess.
Okay, Marina, thank you so much for your lecture. It was really nice. We have a couple of questions here, and also I want to tell everyone that if you have specific questions about this last work, that was Nicolas. He's here to answer, so be my guest to ask anything. So the first question is from Aline, that you know her. When we need to process our data, do we process do we pre-process each data block separately, or we pre-process all the data together? This is the first question.
I would like to distinguish between processing the sample and processing the column. I mean, if you have a spectra and you want to remove, I don't know, scattering or baseline or whatever, then you pre-process each block by itself, choosing what is good for the particular data set. With the column, then it depends, because if you do low-level fusion, and of course you sort of block scale the data, but if you, before dividing by the norm of the block, you want to give a different weight to the variable inside each block, you may also do first a sort of preprocessing of the different variable in the different block. But even if you do a scaling in a distinct way for each block, when you combine the block together, you have to sort of block scale if you want them to contribute in a fair way. So basically, my answer can be you do both if you need.
Thank you, Aline, for the question. And now is Olivia. Olivia is asking, you had said that in low-level data fusion, you have to treat outliers. What are the methods you suggested to treat them, and is it any much better than others?
I mean, for outliers, it's the same as when you do analysis in a single data set. So you can use basically the same methodology, and I think that I mean, doing an exploratory PCA is the best you can do, because then you can look to the residual and you can look to the t-square, and you can see which kind of outlier they are. I personally like a lot exploratory PCA to highlight outlier.
And also, I think we have another question here. Francelson is asking, how can we estimate the contribution of each block in low-level data fusion, and if it's possible to make a variable selection?
This depends on the methodology. For instance, if you use COMDIM, you have the salience, so you have the lambda, and if you use common and distinctive data analysis, you will have some value that tell you if a block was going to 0, which means that this component is distinctive. So basically, for each component, you will have a number that tell you if the block is present or not. And if you just do augmentation, in this case, you can have a look to the loadings, and they will be connected to the contribution of the block. And if you do mid-level data fusion, you basically have the equivalent of the loadings or the PLS weight if you are then using a regression. And this tell you which features are weighting more. But if you really want to know which block, it's better to use methods that are really capable of assessing common and distinctive component. And if you use this coupled matrix factorization, you have also something which is like the lambda in COMDIM. You have a weight somehow that tells you how much the block are contributing. So it's a bit. I know that this is not a shortcut answer because it's different in each type of method.
Yeah, of course. Yeah. And our last question, I think, I don't know if anyone has another question, but it's the Mr. Hyper Tools that we know. Jose Manuel Amigo is asking, Grazie Marina, excellent. A question that comes to me is there any way of handling the analytical error propagation that to assess the final analytical error in the final fused model?
That's a $1 million question.
Yes, exactly.
No, I actually don't know, but I know that there is the possibility of using maximum likelihood, so of using something similar to maximum likelihood PCA if you want to take into account the error. But okay, I promise Jose that during my Christmas holiday I will send him a reference because I'm not an expert, but I sort of remember one reference when I was writing the introduction to my book about this problem of the different type of noise, and was a reference from the somehow more mathematical machine learning community, as far as I remember.
He's saying that so there's something worth to study. Yeah, Jose, you can wait your Christmas present from Marina. It's the reference you want. Okay, if nobody has any questions anymore, I think we are okay. I want to thank you again, Marina, for your time, and everyone that's watching. It's really nice for us. We are starting with the channel, so everything is new, and we are learning a lot about this type of social media stuff. So thank you again very much.
Thank you all.
It was really nice.
And,
yeah, thank you everyone.
Okay, so maybe I borrow a bit more of your time than I was supposed to do.
No,
Forgive me.
it was awesome. It was awesome. Thank you, obrigado.
Ciao a
obrigada
tutti.
a todos. Ciao.
Ciao a tutti. And I hope to see you in a nice conference sooner or later.
Yes, to drink beer presently.
Yeah, and cheers to everyone.
Yeah, cheers everyone. Bye. Have a nice day.
Bye.